All right, kia ora everyone. Without any further ado, it's Gerard.
So I'm going to kick off. I believe in time we will have slides. Please believe with me for a second. E ki ana te kōrero, ko te manu e kai ana I te miro, no nā te ngāhere. Engari, ko te manu e kai ana I te mātauranga, no nā te ao. Tihei mauri ora. Ko whangaroa te moana, ko ohakari te maunga, ko karanghape te marae, ko ngāpui te iwi, ko te whānau pani te hapu. E noho ana au I te taputeranga, ko Gerard Paapu toku ingoa. Kia ora koutou ki ngā ringawera, ngā mihi nui ki ngā kaiwhakahaere o tēnei hui. Nō reira, tēnā koutou, huri noa I te whare, tēnā tātou katoa. No mai haere mai, welcome to domain-specific languages without the boilerplate. Let's skip that. So, why domain-specific languages? I think it's best summed up with this whakatauki, ko te reo te kākahu o te whakaaro. Language is the clothing of thought. There's a lot of deeper meanings to this about culture and provenance, but I'm mostly interested in a very shallow meaning. We really like it when our clothes fit, when they're the right size. And we've found, and all of you every day, even if you're not used to the phrase domain-specific languages, you all use them and you're all familiar with them. But they're typically domains that are outside of our control, things like the DOM. I don't know how many of you are over 30, but when this happened, this was a revelation for web development. We didn't, instead of writing out a long chain of methods, all these impossible, this would be 40 lines of JavaScript if we had to pick through the DOM looking for these specific things. But we had this really expressive domain-specific language for selecting things. And the amazing part was we already knew it because we'd learned CSS. Domain-specific languages can often be much safer than general-purpose languages. I don't think very many of us reach for JavaScript first when we're talking about configuration. If we're storing localization strings, something like JSON, we can hand it to anyone, and we know that the results of passing it broadly are going to be safe. And domain-specific languages, very importantly, afford us multiple interpretations. So often that means that they're flexible about semantics, but even in the case of SQL, I'm sure many of you have written a line of SQL that has a very straightforward interpretation in your head, but when you get it into a query optimizer, you'll find that there's actually hundreds, thousands of ways that the computer could interpret this, and they're vastly different performance characteristics. So these are all domains that are external to us, but the most important domain to each of us typically is our business domain. So I work for an accounting software company, so my business domain is the land of invoices and reports and line items, So when I am writing a business module, I want to talk in these terms and in this vocabulary. But this is where we typically don't use a DSL because it would be something we wanted to build ourselves. And honestly, I think where it trips us up is it's just not that convenient. It's not that cheap to do. It's very cheap to pick up jQuery because someone else has kind of done the legwork. It's very cheap to bring in SQL because you can just pay for it. But if we want to get these same things, if we want something that's expressive and safe and has multiple interpretations, for our own domain, it becomes a lot more expensive. Not always, but I think you'll find that in the languages we're allowed to use at work every day, it's at least seen as expensive. And communities like the Lisp community or Haskell weirdos or the Ruby community, they're much, much quicker than most of us are to reach for a DSL or to define their own DSL. But I don't know about you, but I work in mostly mainstream languages, so languages that are kind of procedural, kind of OOP, and don't have an advanced type system, don't have macros. So I'm talking about C#, TypeScript, Java. That's where a lot of business applications live, and for us, domain-specific languages are very expensive to create. So let's look at why that is. These are the components of a DSL broadly. I'm not going to talk about parsers here because I'm mostly interested in DSLs that live within our traditional compilers, so that live within our application language, not in another file. We're going to have a language that we're writing in, obviously. That's going to be any kind of formal definition. So it might be a type in the application language. It could be a schema or anything else. We need to be able to create scripts that say like programs in our domain-specific language. Typically, when we express them, they're inert. They don't do anything until we interpret them. So in that sense, they are also incomplete. They're not full programs. They are a description of the semantics of our problem that gets reified by an interpreter. So that's going to be a piece of code in Java or in C# or in TypeScript, or I guess JavaScript's a real language, that makes our DSLs happen. So let's look at the traditional cost of doing something like this. This is a really contrived example. Probably not a lot of you are looking at your application code right now and thinking, oh, how do I add numbers? But this is something I could fit on a screen. So we'll see a type definition here. That's the language. So in this type, you can have 3 constructors, essentially. You can construct a value that wraps a literal number, one that expresses addition, and one that expresses multiplication, right? So it doesn't look too arduous yet, but just think about how few semantics are in here and how much we're paying for it. Then on the other hand, we have an interpreter. Again, this is fairly straightforward, but if you imagine that a real problem in your domain, how much work would go into building something like this for it. So let's look at what a script would look like in your program. So if you needed to store in a module somewhere the logic for calculating this, it might look like that, right? So how can we get rid of some of this boilerplate? If you look at the definition of the constructors and then the definition of the interpreters, you can kind of see a chirality there. There's one of them is creating while the other one is destroying. You're building up a tree and you're tearing it down. So, I mean, that's not necessarily a bad architecture, right? We see that a lot. But there is a sort of duplication there that we can seek to get rid of if we want to reduce our boilerplate. Let's imagine instead of providing an interpreter, we just provide the operations of a language. So here we've got a plain object, I think, yeah? And that takes numbers and it calculates numbers. So this is the semantics of the language, but crucially what we've lost here is everything that would make it a script, right? This is using the operations of the application language. We can't introduce another interpretation for this, and it's just doing everything straight away. So we've gained some succinctness, but we've lost a lot of the important qualities. So let's see if we can regain them. We've just turned the object into a type instead of an object, and now we could sub in another object for it. So we take it as a parameter to the script. So we're still expressing the exact same calculation, but now we can decide how we want to interpret it. The problem here is that the return type of this is still number. So the range of ways that you can take 2 numbers, do something called plus to them, and then feel like you've done something meaningful is pretty narrow. So let's take that type out of it. Let's say instead of returning number, we return something. Right? And then I can say, I've got a few different interpreters for this. I can interpret this to number, or big number, or string, or whatever I like. Right? But we're still not quite there. If you're all running a type checker in your head right now, you're very confused because I obviously can't nest these operations. I can't pass the result, a t, into an operation that's looking for a number. Straightforward solution. They all take t's as well. Right? We're getting somewhere. This still doesn't quite work because we have no ways of introducing these number literals in. So we need to get our friend literal back. So this is a functioning example here. What we've got is we've got an expression of that same expression, 3 plus 7 times 4, in a way that we could provide different implementations of this ops object and get completely different interpretations. As a convenience, we can also say that we've expressed, the type calc, which previously we were using for essentially a fancy JSON object, and we were saying this represents an expression in my language, and now we're saying this function represents an expression in my language, and it takes the ops and it turns it into a result, and that result is generic. And we can say an interpreter of these things is a function that takes one of those expressions and then returns some specific concrete type. So here is the original interpreter back. You'll notice that it's a lot shorter because I haven't put as many blank lines in. But one thing that you don't notice straight away maybe is that it's not recursive. None of the functions on this are recursive. There's no tree walking here. There's no awareness of the structure in AST. That saving becomes huge as your language gets more complicated. And it's kind of a straightforward object. It's the kind of API you might have in an object that performs a bunch of operations completely distinct from the idea that you have a domain-specific language. But also, you can add all sorts of different interpreters. Like, if we had started doing this with the old classical interpreter style, you're adding another 30 lines of code or so. Here, you can see that what we're doing is very straightforward. For a lot of our languages, if you said the words, okay, we're using this DSL on the server, people nod along and say, okay, I get it. And you say, then I'm compiling it to JavaScript and passing it to the browser and hoping for the best. People look at you like, oh, I think you're doing something dangerous, something wizardry, like you're doing something complicated. But as you can see here, it's essentially trivial because the recursiveness of the interpreter is gone. We know that the arguments getting passed to us are precompiled, and then we're doing a very trivial pass to say, okay, to express a plus in JavaScript, we put the plus sign between things. We also open up things like this, where we can walk through an expression. So again, we're not really doing the tree walking here, it's implied. But we can collect all the literals that are used within an expression. I've included this example, even though it's a little bit abstract, because, not just because I'm a weirdo, but because these are the types of things that typically people don't get around to writing for internal DSLs. Like, external DSLs usually have really great developer stories, right? You can bring them into your editor and highlight stuff, and it just works. And they can say, oh, how many times do I reference this table in my SQL? And you can find out. But then when you have an internal tool, typically the tools around that are not great. But when you have really cheap multiple interpretation, you get this kind of thing because it stops being difficult. So as a summary, instead of a JSON-y object, the language is a generic interface of methods. The script is a function that consumes that interface, and the interpreter is a concrete instance of the interface that we pass into the script. So I'm going to take this a little bit quicker than I normally would, so if it's less boring, I apologize. We've got a tool internally called date shortcuts that translates phrases like this into concrete dates, because this is how accountants like to write dates. They like to say, okay, 4 weeks after this invoice, because they're doing the same thing over and over again, and the job is very boring. And I wrote a library internally that translates these expressions to real JavaScript dates, right? As anyone would. And laugh if you want, but this was a while ago, and this is what my test suite looks like. Right? I put a date shortcut in, and I get a concrete date out, and I say, it's better be exactly this concrete date. And then James won, sent me a PR, and he said, we really care about internationalization at Xero now, or at least I personally do. And I would like to introduce date shortcuts in Korean. So he did all the work, and he sent me a PR, but in the PR, the test suite basically doubled in size because all my tests were like end to end, right? It was like from date shortcut to finished result. So there was a lot of duplication in there. Around that same time, I started hating native JavaScript dates. I don't know, does anyone here hate them? No, you all love them, right? No? Because they're complicated, right? And I don't care about all this because in accounting, dates aren't all this. Dates are what you can write down with a quill on parchment. They're this, right? Now, this may not be true in physics, but in accounting, this is all we care about. So I wrote a library that did all the math on these, and I wanted to switch date shortcuts over, but if I did that, literally everyone in the company would hate me forever because they would have to switch over. So what I really wanted to be able to do is ship the library with both these features and also at the same time somehow solve the problem of James periodically coming to me with new languages. And this is about when I discovered this technique. Not by myself, I'm going to give you the spoiler later, but essentially what happened is it suddenly became really easy for me to write new interpreters for these date shortcuts. So you can see I've introduced a new interpreter that essentially is only used in debugging and tests that converts the date shortcuts to what I call canonical form. And it's not even a very well thought out format. I can't pass it back in. It's literally just for tests. It's like saying, what do you mean when you put this in? Because it might not be clear to you if you only speak one language what this means, right? But now I can tell because I can convert it to a canonical form. So I can say, when I put this Korean in, I get this canonical form out, and then somewhere else in a completely separate test suite, I'm testing all the date semantics. Now, I didn't invent this. It turns out some other guys did. Please just give me 30 seconds where you don't get caught up in the word algebra, and I swear we'll be through this. But there's this really important paper that came out in 2012, which in computer science is quite young. And it's about a way to represent algebraic structures in these mainstream languages that we're all stuck in. And again, we're really not talking about numbers here. An abstract algebra in the sense that we're talking about is literally, it's a group of elements, so just objects with really no features, and operations that join them. So if you have, for example, dates, and the operations are things like tomorrow from that date, then that joins you to a new date. So any kind of expressive calculation, oh Jesus. We're going to skip over that, no one cares about that. Sorry guys, I'm just a bit short on time right now. So the one rule for object algebras is essentially this. If you're going to return something from a method, it needs to be one of the generic types that you're passing in. And if your method is recursive, or if it would contain a sub-expression, it needs to take that in as one of these abstract types as well. So one of the fun things about these algebras is that they are really easy to extend. So they extend without changing the original type. So you can see here that we've taken the calc algebra, I'm going to be using that naming convention for the rest of the talk, and I've added references, right? So now you've got that same language, but now you can make references to environment variables. And suddenly it's kind of useful, right? This could be a real rule in my application now. So now you're stuck with the problem of, I've got all these little languages, how do I write interpreters for them? And what you can actually do is if you look at this type signature, you're saying we're taking an instance of this more featureful language and we're reducing it to a less featureful language. Sorry, I'm just really tight on time. So what you end up doing is you end up saying, I'm going to interpret the part of this that is only about my language. So you're going to say, I'm going to interpret the references here, and then the rest of it, you can run through the old interpreter, and it should be fine. So that means that you get down to what I was talking about here, when the language fits the problem like a glove, is you can say, for this module, I need these features, and for the rest of the application, I'm going to use this really bare minimum core. And eventually, you reach what I call compositional language design. And it's this idea that instead of writing each new language from scratch as though you had never done it before, you compose a language out of other languages that you've done. So in this case, we can have a language about references. That's the whole language. And we have this language about calculations. And we can combine them ad hoc. So instead of inheriting, we're talking about composition here. And we end up with these tiny little Lego bricks of really commonly used operations, like equality, conditional logic. And when you have enough Lego bricks, you get to build a spaceship. So, sorry, I know we're going very fast, but I'm very short on time because my computer doesn't do anything. So what you can see here is we've built a purpose-driven language out of parts that we may already have lying around at an extremely low cost that we can then combine interpreters to already have like a pre-built framework for running these things. In the beginning, I talked a lot about what we do and don't do in languages, not because it's impossible, but because it is hard. And what I've found is when you make something easier, or let's say cheaper, you don't buy the same amount of it and spend less always. You buy twice as much or 10 times as much and use your same budget. So when you get to a place where defining a new language is something that you can put together from things you have lying around, then you'll find that you put yourself in a mind space where you reach for language-related tools much more often. If this was interesting, but possibly you couldn't quite fit it in your head in 25 minutes, I recommend that you try and remember one of the titles of these talks, of these papers. They're all really approachable. Because they're in mainstream languages, they don't use any features you won't be unfamiliar with. So take a look. Thank you.